Hey there, and welcome to your first video lesson in geometry, or some people call them vodcasts. You may have heard of those. So that's what you'll be doing this year. You'll be learning with vodcasts. So you want to go ahead and get your title down. The title for today's notes is 1.1 and 1.3. Those are the sections in your textbook. And we're doing patterns, reasoning, and conjectures. So the objective is to be able to reason inductively and make predictions about patterns in real-life situations. So what I want you to do now, and every time you watch your video, is go ahead and pause to do your warm-up. So just hit the pause button now, copy all this down, and answer the questions, and then we will discuss them as soon as you hit play again. So, the answer to number 1A is 5, 1, 2, 3, 4. Hopefully you notice that the numbers are just kind of recycling. The 1 goes to the back, and the 2 goes to the back, then the 3. So, on this one, the 4 is going to go to the back, and you're going to have 5, 1, 2, 3, 4. On the next one, the correct answer is 8, negative 12. If you notice, the x values of the coordinates are going up by 2. We have 0, 2, 4, 6. The next one should be 8. And then the y values are going down by 3. 0, negative 3, negative 6, negative 9, and negative 12. Okay, number 2. Is this always, sometimes, or never true? A, if a whole number ends in 2, then its square ends in 4. Hopefully you tried a bunch of numbers. 2 squared is 4, 12 squared is 144, 22 squared is 484, 32 squared is 1024, and they all end in 4. I could keep going all day long, and I bet it would be true. So that is always true. For B, if a square of a whole number ends in 4, then the number itself ends in 2. It's just kind of the flip of what we just saw. So think about some square numbers. What are squares that end in 4? Well, the first one I think of is 64. But the square root of 64 is 8, which does not end in 2. So that is sometimes true, because we did see when you square 12, it does end in 44, or it ends in 4, 144. But when you square 8, it also ends in 4. So this is sometimes true. Last one, if you end in exactly 3 zeros and you square it, it's not going to have exactly 3 zeros. How many zeros is it going to have? It's probably going to have 6 zeros, right? Okay. Okay, so that one is never true. All right, now that we've done that, we're going to go into the notes. So you want to make sure that you get everything down on the notes so that you have them for your notebook check. Example 1, copy the figures and the table. So you want to copy these figures down. You're probably going to need to hit the pause button, but I'm just going to go ahead. Copy this table down, and then copy the instructions. So A is complete the table. So first thing we're going to do is if I have 3 sides on my figure, like this triangle here, how many triangles are formed? Well, there's 1 triangle, so that's going to be a 1. If I have 4 sides, like this square here, then if I draw, this is called a diagonal, if I draw a diagonal, then how many triangles are formed? I've got 2 there. I didn't even hit the button, and that 2 just popped up. Next one is a 5-sided figure. When I draw diagonals, how many triangles do I have? 3. Can you see a pattern here? 1, 2, 3. Let's see, a 6-sided figure. Yep, I get 4. So 7, how many do you think you're going to have? I bet it's going to be 5. Now, next thing we want to do, we're going to get back to this n thing in just a second, part B, we're going to write a formula for the nth term. That means what happens to the number of sides in order to get the number of triangles. Like if I ask you, how many triangles are formed if you have a figure with 782 sides? You don't want to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, all the way till you get to 782. You want a formula that you can use 782 to get to the number of triangles. So what is happening to these numbers in order to get these numbers? The way I like to do this is first I go through a real pattern. I do the same thing every single time, and you'll see that a couple times. What happens to this number? So am I adding or subtracting something to get this number? So 3, if I subtract 2 from it, I get 1. Okay, so let's see if that works here. If I subtract 2 from 4, I get 2. That works. If I subtract 2 from 5, yes, I get 3. So it looks like every time I'm subtracting 2 from the n number to get the bottom number. So my formula is just going to be n minus 2. Now, of course, this rule only works when we're talking about figures, shapes, polygons. So it's only going to be true when n is greater than or equal to 3. Because if you have less than 3 sides, you don't have a figure. So, finally, let's find the number of triangles in the 100th figure. Instead of 782, we'll make it a little bit easier. If you have 100 sides, how many triangles will there be? Well, all we have to do is say 100 minus 2, and we get 98. Very simple. All right, so what we've been doing is called inductive reasoning. Inductive reasoning is making a prediction based on several examples. We saw when it was 3-sided, we had 1 triangle. When it was 4-sided, we have 5 triangles. We had several examples, and finally we came to a conclusion that you subtract the 2 from the number of sides. So let's use a little bit more inductive reasoning to write a formula for the nth term of each pattern, just like we did. So here's a pattern. So like I said, I'm very systematic when I do this. I say, okay, am I adding or subtracting? So let's try that. What do I add to 1 to get 3? Well, I add 2. So let's try. If I add 2 to 2, I do not get 5. So that doesn't work. So addition and subtraction does not work. Let's try multiplication and division. Let's multiply. What do I multiply 1 to get 3? Well, I multiply it by 3. So if I multiply 2 by 3, I do not get 5. So multiplication and division doesn't work. So next thing I do is I try a combination of multiplication and division. So I'm just going to start multiplying by every number. I'm just going to get bigger and bigger until I find the right thing. So let's say if I multiply 1 by 2, then I get 2. Then how do I get a 3? I add 1. So let me see if I can write this out so it's a little bit clearer. So I'm going to multiply by 2 and then add 1. So 1 times 2 is 2, plus 1 is 3. So let's try that here. Multiply by 2, I get 4. That's a multiplication symbol. And if I add 1, I get 5. So far, so good. I'm not going to write it out because I'm feeling real confident now. What's 3 times 2? It's 6. Plus 1 is 7. 4 times 2 is 8. Plus 1 is 9. I've got my formula. So I multiply this number by 2 and add 1. So the formula will be 2n plus 1. Awesome. I got that on the first try. Sometimes it takes a lot more tries than that. That is a linear pattern because these guys go up by 1 every time, and these guys go up by 2 every time. And so you can look here, this looks like a straight line. Hopefully you remember y equals mx plus b. That's a linear pattern. All right, let's see what else we can do. In this one, let's see. I'm going to add 0. If I add 0, it doesn't work. Multiply by 1. Doesn't work. So addition, subtraction, multiplication, division don't work. Let's try a combination. So if I multiply by 2, then I'm not going to write all of these out because this one's actually going to take a while. I have to, let's see, that gives me 2. In order to get to 1, I need to subtract 1. So 2 times 2 is 4, minus 1 is 3. That works. 3 times 2 is 6, but if I minus 1, I don't get 7. So that doesn't work. So let's try multiplying by 3. So if I multiply by 3, I have to subtract 2. So 2 times 3 is 6, minus 2 doesn't give me 3. That doesn't work. Okay, this is getting, I don't like to go this far, but let's try another one. I'll multiply by 4. If I multiply by 4, I'm going to have to subtract 3. 2 times 4 is 8. If I subtract 3, I don't get 3. So I'm not feeling good about this. Let me erase that. Erase that. That does not work. So let's try the next option. So we did addition, subtraction, multiplication, division, and then we did a combination of the two, and none of those work. So this is not going to be linear. So I am going to see if this is an exponent. Or no, I'm going to see if this is a base of an exponent. So like if I square it. If I square 1, I get 1. If I square 2, I don't get 3. So let's try cube it. If I cube 1, I get 1. If I cube 2, 2 times 2 times 2 is not 3. So if I raise it to the 4th power, 2 to the 4th power is not 3. And that is not going to work. Okay, so it's not addition, subtraction. It's not multiplication, division. It's not a combination of the two. It's not a base of an exponent. So let's try making this an exponent. Now this is going to be a little bit strange. You might not have seen this very often. So 2 to the first power. Notice my n is now my exponent. Okay, so 2 to the first power is 2, which obviously isn't 1, but if I subtract 1, then that might work. That'll give me 1. So let's try 2 to the second power. That's 4, and if I minus 1, it works. I get 3. So let's try 2 to the third power. That is 2 times 2 times 2, which is 8, minus 1 gives me 7. So far, so good. Do you know what 2 to the fourth power is? 2 times 2 times 2 times 2, 16, minus 1 is 15. I'm liking it. Looks good. If it works for 4 of them, I believe it. So my formula is going to be 2 to the nth power minus 1. That's a fun one, huh? We probably won't see too many of those yet. You will a little bit later, but just getting you warmed up. Alright, that one is an exponential pattern because your variable is in the exponent. And again, we'll talk more about that later. Okay, now, we are using inductive reasoning to make conjectures. A conjecture is a prediction based on inductive reasoning. So my conjecture was, well, if this is the pattern, then if I raise 2 to the nth power and subtract 1, I'll get my number. So we can write conjectures as conditional statements. When we do that, we're going to have an if part and a then part. So we like to generally say if P, then Q. So it could be if I know the number of sides of a figure and I take away 2, then that will tell me how many triangles there are. So if I have the number of sides and I subtract 2, then I know how many sides there are. Make it real simple. If I live in Conifer, then I live in Colorado. So very simple. Just put an if in front of one part and then a then in front of the other part, and you've got a conditional statement. Now the hypothesis is a name for the if part. You may have heard that in science. In geometry, a hypothesis is the if part of a conditional statement. The conclusion is the then part of a conditional statement. So the hypothesis is I live in Conifer, and the conclusion is, well, if you live in Conifer, then you live in Colorado. Hypothesis, live in Conifer. Conclusion, live in Colorado. So conjectures can either be true or false, conditional statements. They can be switched around, and then we can do all kinds of things with them, and we'll do that later. But just keep in mind that they can be true or false. Now, a counterexample is what you use to make a conjecture false. So if you have a conjecture and it's not true, then it will have a counterexample. So we'll see some examples of that. And I have that there just to see if you can think of any other examples, but you're going to do that at the end of the notes here. So let's look. Identify the hypothesis and conclusion of each statement. If a figure is a square, then it has 4 lines of symmetry. So if a figure is a square. So a figure is a square is the hypothesis, the if part of the statement. Notice my hypothesis does not include the word if. It is just what's ever after the word if. So your conclusion is what's after the word then. It has 4 lines of symmetry. Please remember, do not say, if I say what's the hypothesis, don't say if a figure has a square. Just drop off the if and the then when you're answering that question. Okay, now this one, the expression a minus b quantity squared represents a positive number if a does not equal b. Okay, I don't see a then. The word then is not there, but I do see if. And 99.9% of the time, your hypothesis is after the word if. So if you can restate this as an if-then statement. So if a does not equal b, then the expression a minus b quantity squared represents a positive number makes the same amount of sense as it written this way. So what's after the if is your hypothesis, and then what's left is your conclusion. So kind of reword it in your head and make an if-then statement. And then you'll have your hypothesis and your conclusion. Okay, this guy. People who live in glass houses shouldn't throw stones. No if, no then. So we need to think about this and write it as an if-then statement. So, let's see. What if I said, if people live in glass houses, then they shouldn't throw stones, right? Is that basically what that's saying? If you live in a glass house, you shouldn't throw stones. So I'm going to use that to identify the hypothesis and the conclusion. So I said, if people live in glass houses. So watch how I did this. people live in glass houses. So if people live in glass houses, that's the hypothesis. And then I said if people live in glass houses, then they shouldn't throw stones. So I'm going to throw that little word they in there, and that's going to be my conclusion. So you can kind of edit a little bit. If you don't have an if and a then, rewrite it as an if-then statement, and then you can just very easily identify the hypothesis and conclusion. Okay, last thing, example 4. Tell whether each statement is true or false. And then if it is false, you're going to give a counterexample like we talked about. So the first one, if a person has seen a doctor, then the person has a broken arm. Is that true or false? When we're talking true or false in geometry, it could be true. This very well could be true. I broke my arm, I went to the doctor. But can it all be proven false? Then it's false. Even though it can be sometimes true, we're going to say that it's false. So this guy is false because I just went to the doctor with a sprained ankle. So that's my counterexample. I have seen a doctor, but I didn't break my arm. I sprained my ankle. So you can come up with any counterexample that you want. You had a heart attack. You can use any counterexample that makes this statement false. Mine is I sprained my ankle. I hope I'm not still limping when school starts. Okay, next one. If n equals 3, then 2n minus 2 equals 4. Is that true? Let's see. If n is 3, then 9 times 3 is 6, minus 2 is 4. That is true. If it's true, you're done. Move on. You do not have to provide a counterexample because there is not one. And that is all for the notes. Now, I did include this in here. In your textbook on page 14, there's kind of a cool exploration. It walks you through step by step, and it's using inductive reasoning to make a prediction using these figures. These are called networks, and you're going to decide if you choose to do this. You do not have to do this, but I think it's kind of fun. You're going to decide if these networks are traceable. Traceable means you can use your pen or pencil to go along and never pick up your pencil. Now, I think this one's traceable, but I didn't do it right, so let me try again. And you can go through these networks and see if they are traceable or not. I think you do it this way. Let's see. Down. Nope, I can't remember. See, the thing is, you can't retrace anything. You have to never pick up your pencil and never retrace. So play with these and see if you can find one that is traceable. I know a bunch of them are, a few of them, but I'm obviously not doing it right now. So try them and see what you can come up with and see if you can make a conjecture about how a network is traceable. Okay? All right, finally, you're going to have an out. I want you to write 2 conjectures, one that has a counterexample and one that doesn't. And then for your summary, just give me a brief summary of what you learned. I always provide a comic strip for your enjoyment, and I put a note here that challenge problems are extra credit. I will show you in your textbook next class, but look through your textbook and this homework on pages 5 through 7 and pages 17 through 18, you will see a problem that says challenge. Those you can turn in for extra credit points anytime. You want to do it with a current assignment, but every assignment you'll have some challenge problems that are available for extra credit. So again, we'll talk about that in class. If I don't remember, remind me and I will show you. Okay, that's it for today. So have a wonderful day.